Any questions?
Where's everyone else?
Now, if you ask it again, well, another person.
Where's everyone else?
The magic was used up.
Oh.
Sorry, I used it all.
Actually, I'm surprised that it was not a delayed start, considering it's as if the person who makes the decision looks outside and goes, my driveway's clear.
They canceled school for the.
My
Yeah.
road is not clear.
Good morning.
I guess the magic has a slight delay.
It's like,
All right, for those who missed it, I asked the question of, are there any questions? That's the response I got. All right, so. I have a marker that doesn't work. I have a universe with a charge in it. Doesn't really matter the size of it. I have a universe with a charge in it. It's sitting there. In the words of Jim P12, fat, dumb, and happy. Jim P12 was a guy I worked with. His last name was Shabbatowski. And when he worked the weekends, he'd go in and have to sign in, or the person who's doing security would have to write his name down. And his last name was so hard to spell that it just came down to P12, with 12 letters in it, again with a P. So anyway, fat, dumb, and happy. Sitting there, minding his own business. It's a positive charge. Let's go ahead and emphasize that it is positive. And into this universe appears a negative charge. What is going to happen?
you're going to attract.
Okay. That's what I said last time, and that's what people have been letting us believe for all this time. Let's assume it's true. If they're going to attract, that means that they have to be aware that the other one exists. So how does this charge know that it exists, and this charge know that it exists?
A force of some kind?
Excuse me?
A force of some kind?
Yeah, well, the force requires there to be two charges, but how does one charge know that there's another charge out there in order to exert a force? This is a fundamental philosophical question in physics. And I give you not really a hint, but they made up an answer to start with and then found out that it turned out to be true. Or there's strong evidence to suggest that they guessed correctly. All right, suppose it were pitch black outside, lights were off in this room, like, let's say lights off in the building. You are sitting here in the room, feeling at peace, or alone, whichever way you go. And someone else enters into the room. Will you know another person enters the room?
Yes.
How?
You've heard them?
Like,
The noise they make?
okay. So there's some signal that the person came in, gave off in order for you to sense it. Well, they basically did the same type thinking here. There's got to be something that one of them is giving off that the other one senses, and vice versa. So, what is it that they're giving off? It's not like they have ears or they make noise.
One of the other senses?
What'd you say?
One of the other senses?
No. Well, I'm gonna go with no on that one, but I'm sure there's somebody out there who's made an argument for that. The idea is that before the negative charge shows up, this has to be giving off something. The negative charge is gonna know he exists because of something he's already giving off. So I'm gonna make it look like sort of fumes coming off of it. And the negative charge is gonna show up and it's gonna sense that fume. And it's gonna go, ooh, I like that. Let me see what's there. Because of course, they all have brains that are thinking. Meanwhile, he shows up, he's giving off its own fumes. I usually call them pheromones. And I will be the only physicist probably to call them electric pheromones. But they give off some sort of pheromone that it senses and goes, ooh, I like that. I'm gonna head towards it. And so they're gonna go see what it is. Now, the electric pheromone is not the name that they came up with. They decided to call it an electric field. So that is what an electric field is. It is this field, which is for definition. It is this thing that is given off by a charged object just because it has charge. Now they got really clever with the symbol for it. The symbol for an electric field is a capital E with a vector symbol. How did they come up with this stuff? Now they figured the electric field has to exist with only a single charge there. Force requires two charges, but if I have only a charge in this universe, a single charge, and it's giving off something, it can only depend upon that charge. So what they decided is that, well, I know that the force between these two, so the force on the positive from the negative charge is going to be equal to K, Q, negative Q over R squared. R, let's see, this is the force on the positive charge from the negative charge, R negative hat. Since the electric field can only depend upon one charge, they have to get rid of one of them, so they decide to divide by, well, let's see, we're doing the electric field given off by the negative charge in this case. So we divide by the positive Q, and we're left with this electric field, that's the electric field, of the negative charge is equal to K negative Q, R squared, R negative hat. Likewise, the electric field given off by the positive charge is going to be KQ over R squared, R positive hat. Or, generalized, the electric field given off by some charge is just going to be the electric field. Sorry, the electric field is Coulomb's constant times whatever the charge is, R squared, R hat. So that's the more general formula. Questions up to here? Before I explain something that we've already talked about, except using different language. So if I have enough, oh, actually, one step before that, just don't tell Laura. She's not supposed to know. And not only did I harass you, I gave you an alibi because it's now being recorded. So in our general formula here for electric field, if Q is a positive number, the electric field is in the positive R hat direction, which means away. It's away from whatever that charge is. If Q is negative, then the electric field is in the negative R hat direction, which means towards that charge. So if I have a positive charge here, my electric field lines go away. And if I have a negative charge, my electric field lines go toward. So if I have an electric field here that is moving to the right, I have three different possibilities here. One, I have a positive charge over here. Two, I have a negative charge over here. Or three, which is just a combination of the two, I can have a positive and a negative charge. If I put a proton right here, the stuff that we've already discussed, which way is that proton going to be forced? Why?
Because it goes with the current.
There's no current here.
Pheromones.
Okay. And, oh, I was actually, yes, I was actually thinking of, because positive charges repel each other. So it's going to be forced that way. If I put a positive charge here, which way will it be forced?
Towards
Towards the negative charge. Opposites attract. And if I put the proton here, because it's repelled by the positive and attracted to the negative. In any of these cases, the positive charge goes in the direction of the electric field, as Stephanie claimed. It goes in the direction of the pheromone. Negative charges want to investigate, and so they go up, in a sense, upstream. Positive charges go downstream, negative charges will go upstream in terms of electric field. So we can take the next step in this, is I have an electric field, let's say I have a uniform electric field in this space, and I put a positive charge into it, which way will the positive charge be forced?
Could you repeat that?
If I have a uniform electric field here, going to the right, and I stick a positive charge into it, which way will the positive charge be forced?
To the right.
You disagree? That was, I'm not quite sure I understood.
I was gonna guess the other way, but
Okay.
I'm not confident in that answer, so.
Recognize, in all three of these cases, the positive charge was forced in the direction that the electric field is going. So, the same here. So what we're getting to is that we can now, instead of having to look at the charges and how the charges are distributed, we can look at just the electric field, and we know which way an object's going to be, charge is going to be forced. Stephanie?
Does that electric field in itself have a charge?
No. It is caused by a charge. I'm still going to stick with no, but in about a month and a half, it might seem like I'm contradicting myself. Just a little bit of a teaser. There are two types of current when dealing with this topic. One is you have a moving charge, the other one is you have a changing electric field. The one caused by the changing electric field is known as a displacement current. So, yeah, there it is. That's going to be the confusion in about a month and a half. Other questions? Now, if I wanted to figure out what is the force on this charge, well, let's say my electric field, well, first off, units. What should be the units of an electric field? All the information you need is on the board over there.
Newtons?
Are you stopping there? Or are you tagging?
Yeah,
One of those?
one of those.
You started out right, you then stopped too soon.
We need the direction as well.
No. Just looking for the units of the magnitude.
Newtons per coulomb.
Yes. If you notice over here, force divided by the charge is equal to the electric field, so Newton over coulombs. So the units are newtons per coulomb, the SI units. So over here, if I have a 5 Newton per coulomb electric field, which means there's going to be a force of 5 newtons for every coulomb, and let's make this a 3 coulomb charge. What is the force acting on the charge? Well, I know it's 5 newtons of force for every coulomb, and I got 3 coulombs.
15.
And let's go ahead and make this right positive, so positive 15 newtons. So you can do this from looking at the units, 5 newtons per coulomb times 3 coulombs, or more formally, the force on a charge is equal to the charge times the electric field in which it's bathed. And even though it doesn't necessarily look like it, that's supposed to be an E and that is supposed to be an F. This dramatic pause is for questions and just to let you recover from the absolute magnificence this is. All right, so. If I have 2 positive charges, I know that they will repel. Explanation number 1. Like charges repel. Explanation number 2. Q1 is positive, gives off the electric field away from itself. Q2, positive, senses electric, we'll call that E1, senses electric field 1, and travels downstream. And downstream's in quotation marks because it's just a visual as opposed to there's something actually flowing other than a field. 2 explanations for the exact same phenomenon. Now you might be thinking, man, 2, that's incredible. Are there more? And the answer is yes. We will come up with 2 other explanations for the exact same thing. See a look of excitement on at least one face. 3 faces. 3 faces, 4 faces of excitement. I don't know what you're thinking. You're going, this stuff is great, but can we do a little bit more conceptual grasp of what's going on here? Oh, yeah, let's do a little bit more concept here. Actually, before we do, I guess we can fall into it. I've given problems before. Let's go ahead and let's do a little bit of math here. We'll make that a 5 coulomb charge and a negative 4 coulomb charge, and 2 meters between them. And at point here that is 1.5 meters from the positive charge. What is the electric field? Well, they're vectors, so we add them up. I know that the electric field from the 5 coulomb charge is gonna be going away, so it's gonna be going in that direction. The electric field from the -4 coulomb charge is gonna be going towards it, so it'll be going in the same direction. I'm gonna call that point P. So my electric field at point P is the electric field at point P from the positive charge, plus the electric field at point P from the negative charge. They're vectors, so the total electric field is just the sum of the electric fields. For the positive charge, it's gonna be K, I'll call it Q5, over R5 squared. I know it's to the right, let's go ahead and make it to the right positive. So, positive, plus, from this over here, so K, Q of the 4 over R4 squared. Again, I'm thinking through the directions. I know I can stick in a -4 here, but I know ultimately if the electric field is going to the right, it is a positive number. So I end up with K times 5 over 1.5 squared, plus K times 4 over 0.5 squared. I add them together and I get something spectacular. Let's see, that's gonna be 16K. We have 9/4, 29ths, this is 2.2 repeating, okay. So I get 18.22 repeating times 9 times 10 to the 9th. Newtons per coulomb. It is positive because I've already thought through, I know it's going to be to the right. Whatever that is.
It's a really big number.
It is a very big number. A 1 coulomb charge is huge.